So now that we've finished up our discussion of Project Reactor as used within a single process, it's time to start broadening our horizons and see how reactive programming can be used in a networked environment. And that leads us directly into the topic of SpringWebFlux. And what we're going to do in this lesson is we're going to talk about the structure and functionality of WebFlux as supported in Spring Boot 2.0, which is the current version of Spring Boot. And if you take a look at the Spring Boot documentation, you'll see that there's a couple of different stacks. There's the Spring Web MVC stack or the servlet stack. We've talked about that before, much earlier, like 2 months ago in the course. And now we're going to talk about the reactive stack. So the reactive stack is what Spring WebFlux does, and the servlet stack is what Spring MVC does, or Web MVC. And so we're going to talk about both those things. You can see that they have some things in common, but there's a lot of stuff that's different, and the programming abstractions are quite different. So what is Spring WebFlux? Well, it's as it says here, it's a non-blocking web framework built from the ground up to take advantage of multi-core next-generation processors and handle massive numbers of concurrent connections. So what does that really mean? Well, what it means is they try, because they use reactive types that we have seen already from Project Reactor, they can develop client-server applications, which could actually be multi-tier client-server applications that don't need to block unless absolutely necessary. So the default behavior is not blocking, and that opens up a whole wonderful new world of cool things. Why do we want to do this? Well, one reason is because there's now lots of cores available, so if we can keep things running all these different cores, then we can handle a larger number of concurrent connections. So keep in mind, this is most useful for services, or what we now call microservices, in modern web environments, networked web environments. The way this is handled, and it's really cool, is that requests that come in from a client to a server are computed and handled entirely asynchronously and lazily, which is really absolutely fascinating how this works. So here's an example. Let's say, for instance, we had a request from a client app, like an Android app that was sort of like the Southwest Airlines booking app, if you ever use Southwest Airlines or Expedia or Priceline, or pick your favorite booking app or flight listing app. You might go and say, hey, Cloud, please give me back a list of flights because I want to figure out which one to choose. And again, if you've ever used these apps, you know exactly what they do. You type in your destination, you type in where you're leaving from and your departure, and then you type in the date, and then you say like how many people are going, and you push a button and it goes over to the server, and you get back at some point a list of flights on those dates to those locations. And what we want to do here is make this so that both the client and the server don't have to block. So the client, of course, doesn't want to block because it wants to be responsive to other things. While you make that request, you might say, I decided I don't want to do it. I'm going to cancel. So you want to have control of the GUI so you don't have to wait. You don't have to wait for the results to come back. You can cancel immediately. You can go and navigate to some other part of your GUI. Likewise, on the server, we also don't want to have to block, because if we block, then we have to start using dedicated threads. And we'll see later that that's the old school way of doing things with Web MVC, which requires threads. So what we're doing in this case is we're finding these flights, and we're getting back something right away. We're getting back a flux right away, but that flux actually doesn't necessarily have any values yet. That flux will get values as they are computed by the server. And keep in mind that in a modern multi-tier web environment, what you're likely to see is that there's actually many microservices running in the background that are doing bits and pieces of the work. So for example, if you're going to go and query for flights, if you're using a flight aggregator like Expedia or Priceline or Kayak or whatnot, it's probably actually talking to multiple databases. It's going to go talk to the Southwest database, maybe, or the United database, or the American Airlines database, or the Lufthansa database, or whichever databases are relevant. And each of those things may take different amounts of time to respond. And so what we want to be able to do is we want to start giving results back to the client without waiting for everything to be finished on the server side. And so by using reactive types, that's exactly what we can do. We can give back a reactive type like a flux, and then as results get computed on the server side, they get sent back to the client, but the client doesn't have to wait for everything in order for it to be able to start providing output to the user. So nothing is blocking, basically. Why is this helpful? You can use a smaller number of threads because we don't have to have a thread for every connection. You can have a thread where the threads are typically kind of based on the number of cores that are available. Of course, if you use I/O-bound operations, you may need to have an adaptive number of cores. And by the way, a little hint, there's a scheduler that's part of Project Reactor called Bounded Elastic. And Bounded Elastic is what you want to use by default whenever you have I/O-bound operations, because it will increase elastically the number of threads that are available, taking into account what's blocking and what's not. So it's a little bit like the managed blocker mechanism that's available with Java Common Fork Join Pool. So keep that in mind for assignment 4B, part 1. Another thing you can do with this model is you can actually have non-blocking back pressure that goes across the network. And what that is used to do is it's used to control the rate at which publishers send events so they don't overwhelm slower subscribers. So in the particular example I'm giving here, it may or may not be a situation where the client would be overwhelmed by too many responses from the server. But you can imagine other situations where you're dealing with some kind of sensor, and if it's sending the data very quickly, you might get too much data to keep up on the client side, or the subscriber side. So back pressure is another capability that's built in and it works across the network. Now, the cool thing about this, and what really separates it from Spring Web MVC, which is that other approach we talked about earlier, is that communication across the network uses the reactive types that are defined in Project Reactor. And that, of course, includes mono and includes flux. And there's a few limitations here, which you'll learn about in assignment 4B due to some weirdness about Android at the moment. But in general, if you're not using Android, you can really get true reactiveness on both client and server. So basically what that means is you can have data sequences of either 0 or 1 elements emitted, which is what a mono does, or 0 to n elements emitted, which is what a flux does. And you'll see that you can use these reactive types in your controllers. So remember, the controller is what's exported by Spring such that clients can send it HTTP requests. You saw this earlier in assignment 2 when we were doing the Spring Web MVC model, and you had ways of saying, apply a transform, and you get back a list of transformed images. List is just a basic Java type. The cool thing about WebFlux is you can actually get back reactive types. So here are a couple examples. So we might have an exchange rate service where you give it the currency that you're converting from and the currency you're converting to, and it gives you back a mono to the exchange rate for that particular currency. So that would be an example of a mono. So you get back an object, reactive type that will emit the result once it's computed. Perhaps even more interesting is this example where we have find departure dates, where you're going to give it the departure airport and the arrival airport, and what you're going to get back is a flux of local dates. That's just when there are flights at that particular, for those particular trip legs. And in this case, find departure dates may go out and may search a whole bunch of databases. And so by giving back a flux as the departure dates are discovered as part of the process that's taking place inside the server, the results can start to be fed back to the client. And so the client can start to display the departure dates without having to wait for all the computations to be done in all the places that the server is searching to try to find what the departure dates are from that departure airport to that arrival airport. So that's really, really cool. So that's fluxes, and the get rate thing was an example of monos. And of course, since you've already learned about Project Reactor, you know all the cool things you can do on both client and server with respect to an incredibly rich set of operators. So you can have things like map and subscribe on and observe on and publish on and all kinds of other things. Here's some cool stuff you can do, and this just kind of visualizes what I talked about before. The reactive flux types can actually be streamed element by element. So you can see here we say request airports, So, I want to find a list of airports, or I want to find a flux of airports, and you get back from the server a flux of airports, which again will start being fed back to you right away without having to wait for all the computations to finish on the server to find all the airports that you have. So you don't have to block. That allows clients to be more responsive. Why are they more responsive? They're more responsive because if you used non-reactive types like list, the server would have to build the entire list of airports, and then once the list was built, it would then send the whole list back over to the client. Whereas with a Flux, it can start to stream them back as they appear. So you don't have to wait, and you also don't necessarily have to allocate a giant data structure to hold everything on the server side and the client side. You can stream them back. There's also this concept called live streams, and this is using something called a Spring Server Sent Events annotation. And what that allows you to do is basically it kind of keeps open the connection, if you will, and it'll just keep streaming the results as they occur. So you can keep this open indefinitely, right? It's almost like a Twitter feed. You just keep the stuff coming along, and you never really reach an end until you explicitly end it. If you take a look and you explore the web, you'll find some articles that compare and contrast the performance of the more traditional servlet stacks and Spring Web MVC with the more newfangled, cool reactive stacks, which you find in WebFlux, and you'll see that the performance is typically better, both in terms of how many requests you can process per unit time, and also the response times. And the response times are typically better for the reactive approach because the data can come back right away. You don't have to wait for everything to be buffered up. So take a look at that article if you want to learn more about the pros of the reactive stack versus the servlet stack. That's the end of the overview of Spring WebFlux. We'll take a look at some more examples here in the next lesson.